Oh, hi. I totally didn't see you there. Anywho, I'm going to talk to you about math. Now, you might think math's easy. 1 plus 1 makes 2, blah, blah, blah. But no! Here, we're learning about how to identify perfect squares and square roots. Here, we have a bunch of Legos. They're going to help us solve. Now, I'm pretty sure 37 can't be square, but we need to make sure. One way to check squares is with objects and trying to make a square. Here we go. 1, 2, 3, 4, 5, 35, 36, 37. Bam! Yeah, it's kinda square, as you can see. But now we know for sure. That was checking if a number could be square. But what's a number squared? We will start off easy. A 5. But oh no! It's 5 squared, and we don't know how to solve it. So for this, a key thing. Imagine the number times itself. 5 groups of 5. That's easy. Now it's 5 times 5. So basically, the little tool means multiply by itself, I think. Here, we will use objects again to solve. Let's check with bricks. Making another square, just so we know for sure. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Now, if all was done correctly, we should have a perfect square. Hey, look at that. It is. 5 times 5 equals 25, so 25 is a perfect square. And 5 squared is 25. I'm pretty sure. But wait, there's other ways to solve these kind of things. Let's take a look. Now this way, we must draw and solve equations visually. Let's say we have 84 somethings. We want to see if the somethings could make a square. We could use objects like last time, but that can often take a while. So this, what I'm drawing, is called a factor rainbow. It helps find factors, but we will use it to see if 84 is a perfect square. You would connect all the factors with their match. 1 times 84 equals 84, so 1 connects with 84. 2 times 42 equals 84, and you should eventually get the hang of it. Give me a second, and boom, factor rainbow. Now we must identify a number that could multiply by itself and make 84. Let's see. I can't seem to find one. Let's try to determine if 84 is a perfect square another way, with something called an array. It's sort of like using objects, but on paper. So now, 1, 2, 3, 4, 79, 80, 81, 82, 83, 84. Oh my gosh, that took a while. But as you can see, it is unable to be a perfect square, so 84 somethings cannot be a square. But what about 81? Let's check with our newfound methods. This time, I will start with the array. 1, 2, 3, 80, 81. Wow, it is square. What a surprise. Counting takes breath. But we get to double check. Yay! With the factor rainbow, if that wasn't apparent. So, of course, 81 connects to 1, 27 to 3, and 9. Those are all of 81's factors. Here's the rainbow. And since 9 times 9 equals 81, it is confirmed that 81 is a perfect square. Okay, for this method, we require the prime factors of a number. The factors that a factor tree can no longer break down. We will be figuring out if specifically 324 is a perfect square. So here we go. 324 divided by 2, factor tree, and boom! Here are the prime factors, the circled ones. If we split them into 2 even groups, like this, multiply them, and there we have what we need, 18. And what's 18 times 18? 324. Looks like we have another perfect square on our hands. Why am I doing this again? Because it's fun. Let's try using this awesome method again for 576. 576 divided by 2, 288 divided by 2, 144, 72 divided by 2, and done. Once again, the circled numbers are the prime factors. Using them, we can make two even groups and determine if 576 is a square. So 2 times 2 times 2 times 3 equals 24. And 24 times 24, you guessed it, 576. It is a perfect square. Next chapter. Okay, so now we will be testing ways to estimate square roots. When you don't have the tools necessary to solve exactly, predicting can be important. Predicting accurately is even better. And that's what we will be doing for 56, 234, and 967, which are all non-perfect squares. To estimate or predict, you can use square numbers that are similar to the non-perfect squares or perfect squares you are calculating. So, example, we have 11, but we don't know the square root. So if we know square root of 9 equals 3 and square root of 16 equals 4, both are square numbers, we must determine which one 11 is closer to. So 9 plus 2 equals 11, 16 subtract 5 equals 11. Since 9 is only 2 away, we can assume that the square root of 11 is roughly 3. A viable answer would be between 4 and 3, closer to 3. But it's better to put a decimal, like this. The square root of 11 equals 3.2. The decimal doesn't have to be spot on, but it has to be in the realm of possibility. Now, knowing this, we can try some bigger numbers, like our 56. Some perfect squares before and after 56 would be 48 and 64. 48 is 7 times 7, and 64 is 8 times 8. 48 plus 8 equals 56. 64 minus 8 equals 56. Wow, they are both 8 away. And when stuff like that happens, you know for certain the square root is half, or of 0.5. Since it's between 7 and 8, the square root of 56 is most likely 7.5. Next. 234. Woo. Okay, so square numbers. 225 and 256. 225 plus 9 equals 234. 256 subtract 22 equals 234. The square root of 225 equals 15, and the square root of 256 is 16. So now, a logical number closer to 15. And boom, again. The square root of 234 equals 15.2. Okay, so last, but definitely not least, 967. Square numbers, 961 and 1024. 961 plus 6 equals 967. Then 1224 subtract 57 equals 967. Wow, big difference. Square root of 961 equals 31. The square root of 1024 equals 32. Since 967 is so much closer to 961, the square root should most likely be 31.1. The square root of 967 equals 31.1. So with that, I'm afraid we're going to have to conclude this session. I hope you learned some valuable information today, and I will now be leaving. Goodbye.